We're still talking about our linear functions. So we're still talking about situations where we have a constant rate of change. If we think of the graph, a constant slope. If we think of our direct variation equations, we have a common difference. So we're still talking about those particular situations. We're going to talk about this within proportional and non-proportional relationships. So we first talked about proportional when we talked about our direct variation equations, that those relationships are proportional to each other. So I have my output divided by my input. There's a direct relationship, a ratio, a rate when we talk about those. So a relationship is proportional. It's if its equation is of the form y equals kx, and you've seen this before with our direct variation equations. K cannot be equal to 0, so I'm not talking about a horizontal line here. And the graph passes through 0, 0. So our proportional relationships are very similar and very descriptive as we talk about our direct variation. Very similar in how they work. So we're going to take a look at a proportional relationship and kind of break down the pieces of it. So the table shows the number of miles driven each hour of driving. So if I drive 1 hour, 50 miles, 2 hours, 100 miles, and so on. So we've got three parts to this. First, we're going to be asked to graph the data, and what can we deduce about the relationship. So when I graph this with my hours on my x-axis as my input, my miles on my y-axis as my output, when I graph those points, I see a definite linear relationship there. I could draw a straight line through those points. I'm not, because they only asked us to graph these points here. We're just talking about these points and what relationship we see. I can say that these are definitely a linear relationship. Second question, write an equation to represent the relationship. So now that we've seen that it's linear, we know there is a constant rate of change. We can look for that constant rate of change from our table. So we can look at how is the y value changing compared to the x value. And each of these relationships should be the same. I know we're looking at tables here where the input kind of goes up by a nice even amount. Doesn't necessarily have to be that way. It should be that whenever I divide my change in y by my change in x, which is our rate, or our slope if we think about it that way, then I get the same rate of change. So the rate of change here is always 50. We've got 50 divided by 1, which is 50. 50 divided by 1, I have a consistent rate of change of 50. So I know my rate of change is 50. Rate of change is the same as that k, that constant. So I can plug that into my equation, that my m, my output, equals 50 times h. Whenever I create an equation, I always want to go back and check it with all of the numbers that I've been given. So I'm going to test that out. If I do h times 50, I should come up with the correct miles. So 1 times 50, yes. 2 times 50 is 100. 3 times 50 is 150. 4 times 50 is 200. So this equation does work with this data. And the last question they ask us is use the equation to predict the number of miles driven by in 8 hours. And that's always what we're looking for when we write an equation. We're looking to take that pattern, write a very general pattern, and use it in other situations. So we're using this general pattern that we just created here to help us predict what's coming next. So we want to talk about 8 hours. So our 50 miles times our hours, we plug in our 8 where the h is, and we come up with 400 miles in 8 hours. So these are our proportional relationships. Let's talk about our non-proportional relationships. So we've got this graph here with some points that are plotted. And they've already created the graph for us, and they want us to write an equation in function notation for the graph. Now you'll notice that we can tell right off the bat it's a linear because all of those points line up, but it's not proportional or a direct variation because it does not go through the origin. So since it doesn't go through the origin, it's not proportional. It's also not a direct variation equation. But since it is linear, we can still talk about the rate of change. So we're going to start by finding the rate of change first. So I'm going to plot out my points here and figure out what the table is. And we could also do this as the rise over the run here in my graph. So I come up with a rate of change in my y's is 3, and a rate of change in my x is 1. So again, if I do 3 divided by 1, I get 3 every time. Now again, if this table skipped numbers, if they gave me 1, 3, 5, or they gave me 1 and 2 and then 5, finding the rate of change should still be the same. So for instance, 2 to 5, that is plus 3. 4 to 13, that is plus 9. 9 divided by 3 still gives me a rate of change of 3. So even when I'm skipping from one point to another, I should still have that same rate of change, that same slope. So I've come up with a rate of change of 3. So I'm going to plug that in kind of where my slope goes, kind of where my constant or my rate of change goes in those proportional relationships, and see what happens. I'm going to test this out. Again, you always want to check your equations to make sure they work with the data you've been given. So I'm going to try out y equals 3x. So when I put that back into this table, when I take my input and multiply it by 3, these are the numbers I've come up with. They are not my output that I want. So I want to look and see, is there any pattern that I can figure out to get the output that I've come up with by multiplying by my rate of change, 3, that would get me to this output. And I noticed that all of these are 2 away from my original output. They're actually 2 more. So if I subtract 2 from each of them, that will give me the output that I wanted originally. So I'm going to try out y equals 3x minus 2 and see if that works. So if I test it out with 4, 3 times 4 is 12 minus 2, that gives me 10. 3 times 5 is 15 minus 2, that gives me 15. 3 times 1 is 3 minus 2, that gives me 1. So this is the equation that I'm looking for. This is the equation that represents this particular table. Again, it's non-proportional because it does not go through that origin.